Today we are going to find out what is the optimal choice of consumer. So I start with no slides, and I try to show you how to do things, how to find the optimal bundle for consumers, and then we'll go quickly through the slides. So suppose that I have two goods, X1 and X2. And let's talk about the budget constraint. Suppose this is a budget constraint and it is P1x1 plus P2x2. Let me make it clearer. Equals M. So, what does it mean? The market price for X1 is P1. The market price for X2 is P2. X1 is the number of units of good 1, commodity 1. X2 is the number of units of commodity 2. And M is the income in monetary terms. So actually, if I want to know what is this is every point on the X1 axis has X2 equals 0. So if X2 equals 0, P1 X1 equals M, X1 equals N over P1. And here N over P2. So the slope of this line is actually this over this, which is M over P2 dividing by M over P1 with a negative sign. And therefore the slope is negative P1 over P2. This is the slope of the budget line. So this is actually what this consumer can afford. He can afford to buy anything on this line because he can spend his entire income or below them. So all these are the affordable bundles. And everything here is bundles that you cannot afford. Not affordable. Bundles. And underline this is just affordable. Okay? So typically, if our consumer likes to, his utility is monotone, namely the more the better, then obviously he will actually consume a bundle on this line. Why to be here? He can afford even more on both sides, on both goods. So typically, our consumer will consume a bundle on the budget line. The question is, what is this bundle? So now let me do the same thing here. X1, X2. Here is the bundle. Again, I'll call it M over P1, M over P2. The budget is the same budget. And now let us put what is this in different scale. So let's assume that our consumer has a typical, in different scales, convex, if you like, and let's say this is one of them. And this is another one. So let's say that this is U equals 1. Namely, in every one of the bundles, he produces 1 unit of satisfaction, 1 U type. Utility is 1 in all of these bundles, namely is completely indifferent between all these bundles, each one of them yielding a utility level of 1. Let's say that this is U equals 2. So again, this is an indifferent curve, indifferent scale. He is completely indifferent between all these bundles, and all these bundles yielding 2 units of satisfaction. Utility level is 2, and the assumption is that obviously, I mean, he likes to be here more than he likes to be here. Actually, he prefers every bundle here on every bundle here because it gives him higher utility. So actually, I'm trying to go and to increase his utility. So this is even better for him and he can afford. Why he can afford? Because he can afford, let's say that this is u equals 3, and he can afford buying this bundle and this bundle, or all these bundles. He cannot afford these bundles, he cannot. But he can afford these bundles, this, and everything in between. So he can get a bundle of utility 3. Obviously, he can also afford bundles here of utility 1. The same for utility 2. So my question is, what is the bundle that maximizes his utility, which is affordable? So actually, as you can see, I'm trying to go higher with the indifference curve as much as I can. So actually, the best one will be something that just touches the budget line. Namely, the budget is tangent to the utility level. Let's say that this is u equals 3.5. I can say that this is the optimal bundle for our consumer, and he can achieve utility level of 3.5. And my question is, how to compute this point? And we'll do it in a second. Look, if I move a little bit higher, I'm out. Let's say I move a little bit higher, I cannot, none of the bundles here can be affordable. So what is the affordable bundle that gives me the highest level of satisfaction? Is the one that tangent, that you look on a difference curve that just tangent to the budget line. Okay, so after doing it, let me go back here. Now that we know, I'll put it again in a second, but actually the optimal looks something like this. So this is a difference curve that's just tangent to that. Okay, so now we can see that, but this is exactly the MRS. I mean, what is the MRS? Is exactly the slope of the MRS at a point is just a point where the tangent, you look on the slope of the tangent line that just tangent to the indifference curve. So actually it will be, if it is an interior point, if the best one is a corner solution, we'll talk about separately. But let's say that you get that the indifference curve, the budget line is a tangent line to the difference curve in interior point. What does it mean, interior point? x1 is positive and x2 is positive. None of them are 0. In that case, we can solve it. What we can say, so first of all, the budget constraint is P1 x1 plus P2 x2 equals m. But then I know that the MRS is exactly negative the slope, which is the slope, which is negative P1 over P2. That was the MRS. But I know what is the MRS. The MRS last time is defined as the ratio of the ratio of the marginal utilities. MRS, from last class, it was negative du to dx1 over du to dx2. If I'm given the utility function, I can compute it. Once I compute it, it will be something that depends on x1 and x2. And therefore, I will set it to be equal to negative p1 over p2. And p1 and p2 are given. So I'll get one equation with two unknowns. The two unknowns are x1 and x2. And then I have the budget line, which is another equation, and I will be able to solve. Let me make an example. So suppose we'll start with an example, but then we'll do everything in more general terms. So example, let's take, I don't know, P1 equals 2, P2 equals 3. I just invent now out of my, M equals, I don't know, 12. And let's take a Kapdaglas utility function, u x1, x2, to make it simple, x1, to the half. It's not that simple, times x2. Just as an example. Remember Kapdaglas utility function. We'll have it here. U x1, x2 is x1 to the a times x2 to the b. So our b is 1, our a is 1/2. Okay, so let me find out what is actually the marginal. This is, by the way, is the marginal utility. We called it mu1, and this was mu2. So mu1 is what? Is du to dx1. If I take a derivative with respect to x1, then x2 is like 5. It's a constant. I just vary the x1. So I'll keep x2. But now, what is x1 to the half derivative? It's half x1, half minus 1, namely minus half, times x2. And what is mu2? mu2 is du to dx2. So I keep this constant, and the derivative of x2 with respect to x2 is 1. Derivative of y equals x is 1. Okay. So I'm getting that this is just x1 to the half. So now I know what is the MRS. The MRS is negative. The ratio of mu1 to mu2 is the negative mu1 over mu2. By the way, just to remind you, what is actually the MRS? At a point, I ask, what happens, suppose I want to increase x1 by 1 unit, small unit, by 1 unit by a gram, okay, by milligram. How much I have to decrease x2 so that I'll stay with the same utility level? So let's say that I'm talking about a bundle which gives me a utility of 5 newtons, 5 units, u equals 5. And then my question would be, what happens if I want to increase x1 by small unit, by how many small units I have to decrease x2, so that the new bundle also will have u equals 5. That is MRS, and that depends on the specific bundle. Okay, so now I have to divide this by this, so let me write it. It's minus half x1 to the minus half x2 divide by x1 half. So what is it? It's actually, what is x to the minus half? It's 1 over x to the half. So first of all, the 2 goes down. And this x to the minus half, this is x2. And here I get x1 half, and again x1 half. Why? Because I can put the x1 to the minus half down with a plus. And therefore this is x1, because square root of x1 times square root of x1 is x1. So you add half and half, you get 1. So I'm getting that it is x2 dividing by 2x1. Great. And now the first thing is that the MRS is the tangent of this line, but I know what is the slope of, it is the slope of the tangent line, but I know what is the slope of the line. Is this. So the slope in our case, negative P1 over P2 in our case, in our example, 2 to 3. So it's negative 2, 3. So my first equation is, from here, I conclude that x2 over 2x1 equals 2/3. I simply, this is the minus, I forgot here, minus all over, yeah, because I have minus here. So actually, minus x2 over 2x1 equals minus 2/3. So forget about the minuses, you get this. So I get 4x1 equals 3x2. 4x1 equals 3x2. So x1 I know is 3/4 of x2. Right. So that is just by saying, let me repeat. I take the indifference scalar, okay, and I'm looking, that is, it's clearly this is the best bundle that I can choose. I cannot afford, if I move up with the utility, then I leave this part out, and all the bundles with higher utility, I cannot afford, are not affordable. And I don't want to go below that because I'll decrease the utility. So this bundle gives me the highest utility. Again, what is this bundle? At this point, this is the indifference scale, the tangent line, the slope of the tangent line is the MRS. So I know MRS equals the slope of the tangent line. But what is this tangent line? It's the budget line. And the budget line, I know, it looks like this. What is the slope of this? This over this, which is negative P1 over P2. So therefore, I set up MRS equals negative P1 over P2. I take the minus out, and I get this one. Okay. Now, what is our budget? Our budget line is P1, which is 2, x1 plus P2, which is 3, x2, equals m. What was m? 12. So I can substitute. Instead of x1, I'll put 3/4 x2. So I'm getting 2 times 3/4 x2 plus 3x2 equals 12. So here I have 2 and 4 cancel. I mean, I get 3 and 1.5 x2 plus 3 is 4.5 x2 equals 12. So let me write it down. 4.5, which is 9 over 2. x2 equals 12. x2 star, the optimal one, is 24 over 9. 24 over 9, which is 2 and 2/3. So what is x1 star? x1 star is 3/4 of that. So it is 3/4 of 24 over 9. So this and this cancel. I have here 12, this is 2. So the bundle, this is 2, and this is 2 and 2/3. And I found the optimal bundle. And by the way, obviously, I can just afford it, because if I multiply the price 1 by this and price 2 by 2 and 2/3, I just get 12. So this is an example, and now I want to give you to make everything in a general way that you have also on the slides, and to take Cobb-Douglas utility, and then to see and to understand what is with Cobb-Douglas utility, what is actually your best bundle that that you can afford. Okay, so I do now everything from the beginning with very general way. It will be a little bit technical, but you can follow again and you will see that it's not a big deal. You have it, I believe, in details in the slides. We'll see it together. Okay, I believe that you saw it. I need to erase now what I did, and I'm going to do it in a very general way. So I take it out.